Are you saying the photon from my phone screen and the photon from sun and the photon from the star 10 billion years ago are all secretly one photon? Not in simple sense, not like one tiny glowing ball wearing different costumes. Then why say it? Because the deeper idea behind that statement is genuinely astonishing. It touches one of the most beautiful lessons in quantum physics. A photon is not really an individual tiny object in the way a pebble is an individual tiny object. What we call as many photons may actually be many excitations in a single field, the electromagnetic field. Excitations? The universe may not be made of separate tiny light bullets. It may be made of fields, and photons are temporary ripples in one universal field. Let me start simple. What is a photon? A photon is the smallest unit or quantum of light, and quantum means smallest pieces. In this context, yes, a quantum is one packet of energy. Light does not exchange energy continuously like water flowing smoothly from a tap. And photon means one packet of light. A photon is one packet of electromagnetic field. Wait, you slipped in electromagnetic field. What is that? Right. The electromagnetic field means electricity and magnetism together. The electric field and magnetic field are two sides of one combined thing, the electromagnetic field. In classical physics, light is an electromagnetic wave. It has an electric field and a magnetic field moving through the space together. Classical physics means older physics, before quantum. Yes, the classical physics is the kind of physics that works well for everyday objects, like balls, planets, waves, circuits. Quantum physics, on the other hand, is needed when we go very small, like the atoms and particles. So in classical physics, light is a wave. In quantum physics, light is photons. Yes, but we have to be very careful. It is not that light is sometimes a wave and sometimes a particle because it cannot decide. The deeper view is light is quantum field. Depending on how you measure it, it can show wave-like or particle-like behavior. A photon is not a tiny marble flying through space. A photon is a quantum event in the magnetic field. Quantum event? A quantum event is a single detectable packet. When your eye absorbs one photon, your retina receives one packet of energy. When a camera sensor detects light, it often detects photons as individual hits. Okay, now coming back to the claim, every photon might be the same particle. Where does that come from? There's a famous idea connected to physicist John Wheeler. He once suggested something called one electron universe. I have made a video on it. I'll pin it somewhere in the screen. One electron universe? Yes, the idea was, what if every electron in the universe is actually the same electron moving back and forth through time? This sounds already too complicated. It is more of a thought-provoking idea than standard accepted theory. Thought-provoking means not proven. Yes, a speculative idea. Speculative means interesting, but not established by evidence. So the photon version is similar. Kind of. But with photons, the better version is not the one photon is literally time traveling everywhere. The better version is that all photons are fundamentally identical because they are excitations of the same field. So the same particle line is more poetic than literal. Yes, but it points to something real. In quantum physics, identical particles are not like identical coins. They do not secretly have hidden serial numbers. Serial numbers? Imagine two identical coins made in a factory. Even if they look alike, they look the same. One coin is coin A and the other one is coin B. You can, in principle, track them. But with photons, two photons with same properties are not like that. There is no hidden labeling saying photon number 7392. So nature does not keep tags on photons. Precisely. But if two photons are in different places, aren't they obviously two different photons? In everyday thinking, yes. But in quantum theory, it's different. We'll explain. Okay, in quantum mechanics, particles of the same type are fundamentally indistinguishable. Indistinguishable means you cannot tell them apart. More than that, it is not just that you personally cannot tell them apart. Nature itself does not treat them as separate individual private identities. That is a big claim. It is. Suppose two photons have same frequency, same direction, same polarization. They are in same quantum state. Frequency means color. For visible light, yes. Frequency is how fast light oscillates. Higher frequency means bluer light. Lower frequency means redder light. And polarization? Polarization is the direction in which the electric field of light is vibrating. Imagine shaking a rope up and down versus left and right. Both are waves, but the direction of vibration differs. Okay, so if two photons have all same properties, there is no experiment you can do to say which photon is which. Swapping them makes no physical difference. Like switching two perfectly identical coins, and nobody notices that. Yes, but with real object, swapping matters. If I swap you with me, something has changed. Well, I hope so. But if you swap two identical photons in the same state, nothing physically changes. It's not just ignorance. This is how the mathematics works. Now explain the field theory thing. You keep saying excitation of field. What do you mean by that? Imagine a huge ocean covering the universe. Okay, a wave appears in the ocean. You point and say, there is a wave. Yes. But the wave is not a separate substance from the ocean. It is a pattern in the ocean. Right. Now replace the ocean with electromagnetic field. A photon is like a tiny quantum ripple in that field. So photons are not made of separate photon stuff. They are excitations of electromagnetic field. That's it. Excitation means field is disturbed. Yes, an excitation is raised energy of a field. Like a guitar string vibrating, the strings is the field and the vibration is the excitation. So when I turn on a torch, I'm not creating little balls from nothing. I'm exciting the electromagnetic field. That is exactly the modern view. And when light is absorbed, the excitation disappears from the electromagnetic field and transfers energy to something else, like an electron in an atom. So photon can be created and destroyed. Yes, and this is very important. Unlike some particles, photon number is not always conserved. Conserved means total amount stays the same. Exactly. Energy is conserved, electric charge is conserved, but photon number is not. You can create a photon, absorb photons, split photons like energy into multiple photons in some processes, and combine photons under special conditions. So if photons can be created and destroyed, saying the same photon becomes even stranger. Yes, because in quantum field theory, particles are not permanent little beads. They are field excitations that can appear and disappear based on interactions. So maybe every photon is the same because every photon comes from the same field. Yes, there are many waves, but one ocean. There are many photons, but one electromagnetic field. But a wave in the Indian Ocean and a wave near Japan are different waves. True, and this is where the analogy has limits. So are photons different or not? They can be in different states. State means? A quantum state is the full description of what can be known about a system, its energy, its momentum, polarization, position information if available, and so on. Like one guitar string can vibrate different notes. Yes, if the string vibrates at one frequency, this is one note. At another frequency, another note. The notes are different, but the string is same object. So the electromagnetic field is the string and photons are notes. That is very good image. Earlier you said bosons can pile into same state. Are photons bosons? Photons are bosons. What is a boson? Particles come in two different families, fermions and bosons. Fermions are matter particles like electrons and quarks. They obey 1 per seat rule. Bosons are force-related particles like photons and gluons. They obey the everyone can sit in the same seat rule. What does same seat mean here? Same seat is the same quantum state. So many photons can occupy exact same quantum state. Yes, and this is why lasers work. Lasers. A laser produces many photons in the same frequency, in same direction and same phase. Phase. Phase tells you where in its wave cycle something is. Imagine two people jumping on a trampoline. If they go up and down together, They are in phase. If one go up while the other one is down, they are out of phase. So lasers, photons are highly coordinated. Highly coordinated. A laser is like a huge cloud of photons marching in step. And because photons are bosons, they're allowed to crowd into same state. Yes, in fact, photons like doing that. The presence of photons in a state makes it more likely that more photons will join that state. This is called stimulated emission. Stimulated emission? It means the incoming photon can stimulate an excited atom to emit another photon matching it. Same frequency, same direction, same phase. This is the core mechanism behind lasers. So a laser is a kind of best example of photons losing individuality. Yes, a laser beam is not like a stream of, labeled photons. It is more like one shared quantum mode filled with many photon excitations. Quantum mode? A mode is a specific way a field can vibrate. Like a guitar string can vibrate in different patterns, each pattern is a mode. So a photon number in a mode means how many energy packets are in that vibration pattern. You got it. Let me challenge this. If I have two photons, one red and one blue, they're not the same. They are of the same type of particle, but they are in different states. Like two songs played on the same instrument. Yes, same instrument, different notes. What about photon from Big Bang and a photon from my phone screen? Same field, same particle species, different states, different histories, different energies. I still feel like identity should be real. If one photon leaves the sun and another leaves a lamp, surely they are two different things. That intuition comes from everyday objects, obviously. Everyday objects are made of many particles arranged in a specific way. They have histories, they have scratches, shapes, locations, and memories of interactions. But the fundamental particles do not have individuality like that. Why not? Because there's no hidden physical property that distinguishes one photon from another photon in the same state. Can't we track its path? Sometimes approximately, but in quantum mechanics, a particle does not always have a definite path between emission and detection. That's weird. In double slit experiment, light or particle pass through narrow opening and create interference pattern. Interference means adding and cancelling. Yes, if two wave peaks meet, they add. If a peak meets a trough, they cancel. But individual photons also create the same pattern over time. Yes, even if you send photons one at a time, the final pattern builds up like a wave interference pattern. So each photon seems to behave as if it went through both slits. That is one way to say it. More carefully, the quantum state includes multiple possible paths, and the probabilities interfere. So assigning a little private route to each photon is not always valid. Yes, and this is why photons' identity is slippery. You mentioned about possible paths. Is this Feynman stuff? Yes, Richard Feynman stuff. He developed a way of doing quantum physics called path integral. Path integral? It means that to calculate what a particle does, you consider all possible paths it could take, not just one path. All possible paths, like literally every route. In the calculation, yes, a straight path, a curved path, strange path, paths that go far away and come back. Each path contribute a little mathematical amount. And the final result comes out adding them. Yes, some paths reinforce each other, some cancel out. So when a photon goes from a star to my eye, it is not simply one tiny ball moving on an obvious line. Correct. The final destination event is produced by a quantum probability pattern. People also say that photons do not experience time. Is that connected? In special relativity, objects moving at the speed of light have zero proper time along their path. Proper time? Proper time is the time measured by a clock moving with the object. So if I carry a clock, proper time is what my clock measures. Yes. And for a photon travels at the speed of light and the mathematical interval along the path is zero. So people say a photon experiences no time. A photon does not have a valid rest frame. Rest frame? A rest frame is a viewpoint where an object is sitting still. You have a rest frame. A car has a rest frame. A massive particle has a rest frame. But a photon cannot be at rest. There is no viewpoint where you can ride next to a photon and see it stationary. So asking what does a photon experience is not really a valid question. Yes, it's more poetic shortcut, but not a proper description. But the zero proper time idea makes photons feel timeless. Yes, and that adds to the mystery. A photon emitted by a distant galaxy may take billions of years in our frame of reference to reach us, but along the light like path, the proper time is zero. Light like? A light like path is the path followed by something moving at the speed of light. In space-time diagram, it sits exactly at the boundary between slower than light and the impossible faster than light paths. So from our viewpoint, ancient photons travel for billions of years, but photon itself does not have a clock. Correct. Could one photon be everywhere at once? A single photon can have a spread out quantum state. Spread out. Yes, a photon's quantum state can be spread out over space. Until it is detected, it may not be localized to one tiny point. Localized means pinned to specific place. Yes. So one photon can be spread across large region. In some cases, a single photon can be described as a wave packet spread over many kilometers or more. A wave packet? A wave packet is a localized bundle of wave behavior. It is not infinitely spread out like a perfect wave, but not a tiny dot either. So the photon is not necessarily here or there before detection. That's right. But that is still one photon, not all photons. Correct. One photon can be spread out, but that does not mean that one photon equals every photon in the universe. You said photons can be created and destroyed. That feels important. An atom is excited when one of its electrons has extra energy. When the electron drops to a lower energy level, the atom releases extra energy as a photon. So, photon created. A photon is created. When your eye absorbs a photon, that photon transfers its energy to molecule in your retina. And photon destroyed. A photon destroyed. But if particles can appear and disappear, what remains permanent? What remains permanent? The field remains permanent. Energy is transferred. Charge is conserved. Momentum is conserved. But the number of photons can change. Momentum? Think about momentum as motion quantity. For everyday object, it is mass times velocity. Photons have momentum even though they have no rest mass. No rest mass means? Rest mass means the mass of an object when it is not moving. Photons cannot be at rest, so they have zero rest mass. But they still carry energy. They still carry the energy. A photon's energy depends on its frequency. Higher frequency, higher energy. So blue light has more energy per photon than red light. Correct. Does this apply to electrons too? Partly. Electrons are also excitations of electron field. So all electrons come from one electron field. Yes, in quantum field theory, every particle type corresponds to a field. Then why focus on photons? Photons are especially easy to create and destroy, and because they are bosons, many photons can occupy the same state. Remember the laser? And electrons cannot? No, electrons are fermions. They obey the Pauli exclusion principle. It says fermions cannot occupy the same quantum state. And that is why atoms have structure. Exactly. Now think about it. If all electrons could fall into same lowest state, chemistry would collapse. The periodic table exists because electrons are forced into different states around atoms. So fermions create structure by refusing to share states. Beautifully said. And photons can share states, which creates lasers. Precisely. This is changing the picture. We think the universe is made of particles. You're saying it is made of fields. That is the modern physics picture. So what we call particle is just field doing something. Yes, a particle is a quantized excitation of a field. Quantized? Quantized means it comes in discrete chunks, like stairs, instead of ramp. So a field cannot always have any amount of energy. In each mode, the energy comes in specific steps. For light, each step corresponds to one photon. Okay, so one photon means one step of energy in an electromagnetic field mode. So maybe the universe is not box filled with tiny objects. Maybe it is a set of fields, and objects are patterns in those fields. That is the heart of quantum field theory. Okay, let me try saying it. Every photon is the same particle in the sense that every photon is an excitation of same electromagnetic field, and photons do not have individuality or individual identity tags. Perfect. But not in the sense that one photon physically travels from Big Bang to my torch to a distant star and becomes all photons. Correct? But could there be a deeper theory where it is literally one photon? We do not have evidence for that. It is better not to claim it. Physics is already strange enough without exaggerating. Is there any experiment that shows photons are indistinguishable? Yes, one famous example is Hong-Ou-Mandel effect. And that name sounds like a law firm. It does. It's an experiment of two identical photons arriving at a beam splitter. Beam splitter? A beam splitter is an optical device that partly reflects and partly transmits the light. Imagine a glass plate that gives light two possible exits. Okay. If two identical photons enters the beam splitter from two different sides, exactly the same time, quantum mechanics says they do something very surprising. They bunch together and they leave together instead of separately. Why? Because the two possibilities interfere. Photon 1 reflected and photon B transmitted, or photon 1 transmitted and photon B reflected. But because the photons are indistinguishable, nature does not label which one is which. The alternatives cancel in one outcome and reinforce another. So the experiment only works because photons have no identity tags. Exactly. If the photons were indistinguishable, different color, different timing, different polarization, the effect weakens or disappears. That is a strong evidence that which photon is which is not a meaningful question. Yes. Okay, now connect this to history, like every photon in history. Think about light from the early universe. You mean cosmic microwave background? Well, the cosmic microwave background, or CMB, is ancient light left over from when the universe became transparent about 380,000 years after the Big Bang. Transparent meaning light could finally travel freely. Light could travel freely. Before that, the universe was a hot plasma. Plasma? Plasma is a state of matter where electrons are separated from atoms, so charged particles move around freely. The early universe was full of charged particles, and photons kept scattering of them. Scattering means bouncing or changing direction due to interaction. Yes, and photon could not travel far without hitting a charged particle. Then the universe cooled. Yes, the universe cooled. The electrons joined the nuclei to form neutral atoms. Light could finally travel across space. That ancient light is still around today as microwave. So some photons we detect today are extremely old. From our frame, yes. But those photons are still the excitation of the same electromagnetic field as photons made by my LED light. Exactly. A microwave photon from early universe and a visible photon from your phone are different states of the same field. So why does this idea feel so deep? Because it attacks our everyday intuition of thingness. Thingness? That belief that reality is made of separate little things, each carrying its own identity. Like this cup is this cup, that chair is that chair, this photon is this photon. Exactly. But at the fundamental level, identity is not so simple. Particles of the same type are not individuals in the everyday sense. They are repeatable excitations of the field. So the universe may be less like a pile of objects and more like music. Yes, different notes, same instrument, different particles, same underlying fields. That is actually beautiful and unsettling because it means many things might be just one thing behaving in many ways. So maybe history was never filled with countless separate photons. Maybe it was filled with one field vibrating in countless ways. And every time we see light, we are not catching a tiny object. We are witnessing the electromagnetic field hand us one packet of energy. A photon. A photon. So maybe the real question is not how many photons are there. Maybe the real question is how many ways can one field shine? Thanks for watching.